Hello, welcome to CS with Terry. Today we are going to talk about binary search. Binary search is used to find a specific element in a sorted array. Many people think of binary search as one of the easiest algorithms. However, its implementation is prone to mistakes, especially in the treatment of boundary conditions. The famous computer scientist Donald Knuth once said, "Although the basic idea of binary search is comparatively straightforward, the details can be surprisingly tricky." Today, we will try to find a simple yet universal algorithm to solve most binary search problems. Let's take a look at this example. Given a sorted array where the elements are 1, 2, 3, 5, 5, 5, 8, 9, there are 4 subproblems. First, find the first element greater than or equal to 5. Second, find the last element less than 5. Third, find the first element greater than 5. Fourth, find the last element less than or equal to 5. Let's see what the answers to the 4 questions are, respectively. There are 3 5s in the array, so the answer to the first question is the first 5. The answer to the second question is the element before the 5s, which is 3. The answer to the third question is the element following the 5s, which is 8. And the answer to the fourth question is the last 5. We can see that the 4 questions look quite similar, but differ slightly in details, which results in completely different answers. If we use binary search to solve this problem, we could easily make mistakes in its implementation. Let's forget the previous questions for a minute and look at binary search from a different angle. Shown here is an array with n elements. These elements are indexed from 0 to n-1. In the n elements, the first k elements are blue, while the rest are red. However, the border between the red and blue elements is unknown, which means k is unknown. In other words, the entire array is gray when we first see it. We would like to identify the border between blue and red elements. In other words, we'd like to solve the unknown variable k. Let's first take a look at the brute force method. Here, suppose there is an array with 9 elements, where the first 5 elements are blue and the rest are red. The entire array is gray when we first see it. We can design a blue pointer. It points to the leftmost position first, and then keeps moving rightward, until it touches the border between blue and red. Similarly, we can design a red pointer. It points to the rightmost position and keeps moving leftward until it touches the border. We can identify the border between blue and red elements in this way. Of course, this algorithm is not very efficient. Its time complexity is O(n). Now, let's use binary search to identify the border efficiently. In the brute force algorithm, we keep moving the blue pointer towards the right. This process is essentially extending the blue region. Similarly, the process of moving the red pointers towards the left is essentially extending the red region. The reason that the brute force algorithm is so inefficient is because the blue or red regions are extended slowly, one element at a time. Is there a way to accelerate extending the blue or red regions? We can do this. We can check the color of the element in the centermost position of the array. Here, we can see the element is blue. What does the element being blue imply? It means this element and all the elements to its left are blue. Then, we can extend the blue region all the way to this element. If we continue this operation by checking the color of the elements in the centermost position of the gray area, we can see it is red, which means this element and all the elements to its right are red. Then, we can extend the red region all the way to its position. We can repeat this operation until we find the border of the blue and the red regions. This is the binary search algorithm. Now, let's go through the pseudocode of binary search. At the beginning, we create 2 pointers, L and R. L points to -1 and R points to n. The 2 pointers represent the frontier of the blue and red regions. Then, if L plus 1 does not equal to R, the algorithm will enter the loop. We'll obtain the position of the element in the center of the gray region, denoted as M. and m equal to L plus R divided by 2 and then take the floor. If m is blue, we will let L equal to m. In other words, extend the blue region to m. If m is red, then we will let R equal to m. In other words, extend the red region to m. We will repeat this process until the condition L plus 1 equal to R is satisfied. We will find L and R right at the border between the blue and the red regions. We can decide whether to return L or R depending on the actual problem. Now, let's review what this program does. We start by designing two pointers L and R. L points to the blue region and R points to the red region. With binary search, L and R quickly approach the border between blue and red regions, while maintaining their colors. This is critical. Let's highlight this sentence. In the end, L and R will be right at the border between the blue and the red regions. We can return them. The time complexity of binary search is O log n. Because we reduce the length of the gray region by half in every iteration. Thus, we need about log n times to reduce the length of the gray region to 0. The binary search algorithm we just introduced might be slightly different from the versions you might have seen elsewhere. Let's dig deeper and look at a few details to prove the correctness of the algorithm. Let's look at the first detail. Why are the initial values of L and R -1 and n? Can we initialize L to be 0 or R to be n-1? The answer is no. Suppose the entire array is red. Then, if we initialize L to be 0, L will be in the red region, which is wrong. Similarly, if the entire array is blue, then if we initialize R to be n-1, R will be in the blue region, which is wrong. This is why we need to initialize L to be -1 and R to be n. Now let's take a look at the second detail. Is m always in the left closed right open interval between 0 and n? First of all, why are we asking this question? As we can see, in our program, we need to check the color of the element m points to. This is only meaningful if m lies in the left closed right open interval between 0 and n. But, does it? Let's first calculate the lower bound of m. Since m is equal to L plus R divided by 2, if we want m to be as small as possible, we need L and R to be as small as possible. The minimum value of L is its initial value, -1. The minimum value of R is 1 if the program is to enter the loop. Why is the minimum of R 1 instead of 0? Because if R is equal to 0, L plus 1 is equal to R, then the program would exit the loop. Since the minimum of L is -1 and the minimum of R is 1, we can calculate the minimum of m, which is the sum of L and R divided by 2 and is equal to 0. Now, let's look at the upper bound of m. Similarly, if we want m to be as large as possible, we need L and R to be as large as possible. The maximum of R is n. For L, if the program is to enter the loop, its maximum should be n-2. Then we can calculate the maximum of m as the sum of L and R divided by 2, which is n-1. In summary, the minimum of m is 0, and the maximum is n-1. So m will always stay in the left closed right open interval between 0 and n. In other words, it will not overflow. Now, let's look at the third detail. When updating the pointers, can we let L equal to m plus 1 or R equal to m-1? Binary search algorithms you see elsewhere often do this. However, those implementations are prone to mistakes. For example, if m happens to point to the last element in the blue region in an iteration, then L would point to the red region if we let L equal to m plus 1, which is wrong. On the other hand, if m happens to point to the first element in the red region, then R would point to the blue region if we let R equal to m-1, which is also wrong. Granted, if we implement the algorithm carefully, letting L equal to m plus 1 or R equal to m minus 1 will also give us the correct program. But letting L equal to m and R equal to m is easy to understand and less error-prone. Let's look at the fourth detail, whether the program will go into an infinite loop. Let's consider the following scenarios: L plus 1 equal to R, L plus 2 equal to R, and L plus 3 equal to R. In the first scenario, L plus 1 equal to R, the while loop would terminate immediately. In the second scenario, L plus 2 equal to R, there is one element between L and R. When the loop starts, we calculate m to be the sum of L and R divided by 2. We'll see that m is exactly the element between L and R. Then, we will either let L equal to m or R equal to m, which means when the iteration ends, we will arrive at the first scenario and exit the loop. In the third scenario, L plus 3 equal to R, the program will arrive at scenario 1 or 2. You can think about it. You can also think about more scenarios. This proves that whatever values L and R take, the program will arrive at scenario 1 and exit the loop. Okay, now it's time to unveil the answers. At the start of the video, we asked 4 questions. Here are the corresponding answers. The first question is to find the first element greater than or equal to 5. We can assign blue and red regions like this. Let elements less than 5 be blue, elements greater than or equal to 5 be red. The condition for is blue is less than 5. The program returns R. The second question is to find the last element less than 5. The blue and red region assignment is the same as the first question, but we need to return L. The third question is to find the first element greater than 5. We can assign the blue and the red regions like this. Let the elements less than or equal to 5 be blue, and elements greater than 5 be red. The condition for the isBlue function is less than or equal to 5. The program returns R. The last question, find the last element less than or equal to 5. The blue and the red region assignment is the same as the third question, but we need to return L. By the way, there are functions in the C++ standard library that can solve the above questions. We can use the function std_lowerbound to solve the first question. The answer to the previous question -1 solves the second question. We can use the function std_upperbound to solve the third question. And the answer to the previous question -1 solves the fourth question. Now, let's summarize the general procedure to solve a binary search problem. Firstly, we'll need to build a simple model. In other words, we need to divide the array into blue and red regions and define the function isBlue. Secondly, we will need to decide whether to return L or R. Then, we can simply follow the algorithm template. Finally, we can add some post-processing steps if necessary, depending on the application. Okay, this is all on binary search. Before the video ends, let's think about the question. The binary search algorithm we introduced today is used to find a specific element in an array. In other words, the indices of the array are integers. But can we apply binary search to floats? For example, is it possible to calculate square root of 2 with error less than 10 to the power of -6 using binary search? Thank you for watching. If you like this video, please subscribe to our channel, press the like button, and share it with your friends. See you next time!